Hi guys, welcome to Safi Mixed. In this video, I want to solve Schrodinger wave equation for the problem of potential step as a part of our previous videos for the case when the energy of the incident particle is greater than the height of the potential, and we'll see what's the difference between the quantum mechanical solution and the result of classical approaches. And to that end, I just want to begin from the geometry that we used in our previous videos. I consider potential step at x is equal to 0 of height v naught that is, we divide the whole space into two regions, region 2 and region 1. To the left it is region 1, and to the right it is region 2. And in region 2 we have a potential of magnitude or height v naught, and to the left the potential is 0. And we consider a particle that incidence on the height such that E is greater than V naught. So the incident energy of the particle is greater than the height of V naught. And we want to solve the Schrodinger equation, the time-independent Schrodinger equation for this case. So I'll borrow some equations from the previous videos. So we consider this case that E is greater than the height of the potential. The energy of the incident particle is larger than the potential. Then in this region, as you may recall from the previous video, that this wave function psi1 of x over dx squared plus k1 squared psi1 of x equals 0, where k1 square, I use this later on, so I would write this word here, was defined to be 2m e divided by h bar squared. This is the parameter, the energy parameter. I call this energy parameter because k1 depends on energy, so the energy parameter was defined to this one equation. And we found that the general solution to the wave function is in fact given by psi1x equals a exponent iota k1x plus b exponent minus iota k1x. This was the general solution to the wave function in region 1, where this part defines the incident wave and this part defines the reflected waves. That is, the incident wave is given by psi incident. I can write this equal to a times exponent iota k1x, and the reflected wave psi reflected is given by b times exponent minus iota k1x. And then for the solution, or for the time-independent Schrodinger wave equation in the second region, we wrote it like this: d squared psi2 of x divided by dx squared minus 2m divided by h bar squared into v naught, or v of x minus e psi 2 of x equals 0. This was the form of the Schrodinger wave equation in region 2 when V naught was greater than E, and now we are solving it for E greater than V naught. I think I call it Vx, not V naught. In the previous I call it Vx, something like that. But don't be confused with the notation. So I can take the minus sign out of these two terms and can put the equation. This would become plus, and I would reverse these two to write it in this form: E minus V naught. And then we defined an energy parameter K2 in the form K2 squared equals 2m divided by h bar squared into E minus V naught. I'll use this one as well later on, so I put that for the record over there. And if I use this thing, I can replace this equation in the form k2 squared psi 2x equals 0. Now I can write the root equation for this and can put this in the form 2 squared plus k2 squared equals 0, or d equals plus minus iota k2. That means we have two solutions to this one equation, one for the positive root and one for the negative root, and the generalized solution should be a superposition of these two. So I write, like in the case of, and the generalized solution should be the superposition of these two, like this one. So I write psi 2 of x would be equal to c times exponent iota k2, x1 for the positive value, and plus d exponent minus iota k2x. This is the generalized solution for the wave function in region 2. And again, this part describes the wave transmitted or the wave traveling in the forward direction along the positive value of x, and this one defines the wave traveling backward. But in the region 2 there is no boundary, and if there is no boundary, that means no wave will be reflected in this one direction. So this part must be 0. There is no wave traveling in the backward direction or opposite to the x-axis. So that means the coefficient, the d, should be equal to 0, and I said this equal to 0. That allows me to write psi 2 x as c times exponent iota k2x. So now we have two solutions, one defining the dynamics in region 1 and the other defining the dynamics in region 2. So and both contains unknown parameters, unknown probability amplitudes A, B, and C. So we need to fix the value of A, B, and C in terms of the energy parameters K1 and K2. And that we can do by using the continuity conditions on the wave function on its derivative. So I first write this equation for references. At this position, psi 2 of x equals c times exponent iota k2x. Okay, now according to continuity condition on the wave function, the wave functions in the two regions at the boundary must be continuous. That is, psi 1 of x at x equals 0 must be equal to psi 2 of x at x equals 0. And that means we should have a exponent iota k1x plus b exponent minus iota k1x at x equals 0 to both of them must be equal to c exponent iota k2x at x equals 0. Now if I put the value of position in the boundary, I get this term, the exponent would give me 1, this exponent would give me 1, this exponent gives me 1 because x0. So I write this as a plus b equals c. This is one equation that links the probability amplitudes in the two waves with each other. And now, using the second condition, that is the derivative of the two wave functions must be continuous at the boundary, means the derivative d psi 1 over dx at x equals 0 must be equal to d psi 2x over dx at x equals 0. So if I put the values in this side, I would have the derivative of this exponent plus the derivative of this exponent, and we see the derivative of exponent iota k1x is in fact equal to iota k1 times back this function. So if I put the values, the derivative of this I1x gives me a times iota k1 into exponent iota k1x, and the derivative of this gives me b times iota minus iota k1 into exponent minus iota k1x for this, and then equals, and the whole of this is the boundary x equals 0. And now if I put the value of this wave function at this position, I just get from this c times iota k2 into exponent iota k2x at x equals 0, and put x equal to 0 at this side and this side. This exponent would become 1, this exponent would become 1, and similarly this exponent for x equal to 0 becomes 1. So it gives me I can take iota k1 common from these two terms, and can write iota k1 times a plus b equals iota k2 times c. And I can cancel iota on both sides, and that allows me to write a plus b equals, this is minus not plus, this is minus, so I should use minus here, minus b equals k2 over k1 times c. Okay, now I have two equations, one this one and the other this one, and both of them link the probability amplitudes, but there are three unknowns, so we want to solve these two equations for c and b in terms of a. And that I can do by putting the value of c from this equation into this equation to eliminate c. So I write a minus b equals k2 over k1 into, for c I write a plus b here, so that gives me a plus b. And now I can take b to the left side of this equation and can write this as minus b, and if I multiplied this with this, that would become k2 over k1b, and then I'm taking it to this side, so that allows me to write 1 plus k2 over k1. And similarly to this side, I would be able to write this with this, and I'm taking a common, and this will become minus, so I write k2 over k1 minus 1 into a. Or I take this to take the LCM, it will be k1 plus k2 divided by k1, in here k2 minus k1 divided by k1, so I can cancel k1 from the denominator and can write b is, let me do this here, I rub this out, and I write minus b into k1 plus k2 divided by k1 equals k2 minus k1 divided by k1 times a. I cancel this out, and I can write, if I take this minus to this side, it will become k1 minus k2, so I write b equals k1 minus k2 divided with k1 plus k2 times a. So this is the value of b, and I want to write this value. I don't need in this equation, so I want to write this value for lateral loose is k1 minus k2 divided by k1 plus k2 times a. Okay, next I want to use the value of b, this value, in this equation and solve it for c. So let me put this value at this position to write it is A minus K1 minus K2 divided by K1 plus K2 times A equals K2 divided by K1 times C. And from this I can write A, and here would be 1, and I take the LCM to write this K1 plus K2, and this minus multiplied with this would make it K1 plus K2 and the whole divided with K1 plus K2, and this equals K2 over K1 times C. Let's cancel with this. These two become 2K2, and I write A times 2K2 divided by K1 plus K2 equals K2 divided by K1 times C. I can cancel this K2 with this K2 and taking K1 to this side, and then inverting the whole equation would allow me to write this as 2K1 divided by K1 plus K2 times A. So I write this value here. C equals 2 times K1 over K1 plus K2 times A. I don't need this equation anymore, so I rub them out. Okay, now you see, we have defined the probability amplitude B and C in terms of the energy parameters K1, K2, and in terms of the probability amplitude of the incident wave. We can find A by normalizing the incident wave, but that is not needed because you will see in the coming equation A eliminates, so we don't need the information of A anymore to understand the dynamics of the problem. So what I do, I next find the transmission and reflection coefficients of the transmitted wave into this region, and we see the transmitted wave which is given by psi transmitted equals C times exponent iota K2x. That was the value of psi transmitted. And in order to find T and R, I need to find the probability current density, and by definition the probability current density is given by iota h bar divided by 2m into psi of x into derivative of the conjugate of psi of x minus conjugate of psi of x times derivative of psi of x. Now I can find the current density, the probability current density for incident wave, for reflected wave, and for transmitted wave. And I want to do that just for the incident wave first. So for the incident wave, I get JIM equals iota divided by h bar divided by the 2m into the value of psi x, which is A times exponent iota x, iota k1x. Then psi steric would be A times A minus k1x, and the derivative of psi steric would become A mod A steric into minus iota k1 exponent minus iota k1x, and then minus, for this it will become A steric exponent minus iota k1x multiplied with A times iota k1 exponent iota k1x, because this thing, the derivative of this gives me this thing. So now this minus exponent and this minus exponent gives me 1, and similarly this minus exponent in this minus this plus exponent multiplies to give me 1. What I do have minus iota k1x and minus iota k1 is A times A steric would give me A mod square A steric times A would give me A mod square. So this is in fact iota divided by h bar divided by 2m into 2 times minus iota k1 A mod squared. I can cancel this 2 with this 2, and iota times iota gives me minus, so that minus multiplied with this minus gives me plus. So I write this thing is h bar k1 divided by m into A mod squared. That is, the incident probability current density is in fact is directly proportional to the mod A mod squared in terms of the K1, which is energy parameter. And similarly, if you put the values for reflected wave, you would be able to write J or EF. That you can do as an exercise. Just plug in this value to this equation and you will get minus h bar k1 divided by m b mod squared. And similarly, if you plug in the transmitted wave into the definition of probability current density, you would get J transmitted equals h bar k2 divided by m into c mod squared. So we have the probability current densities for the incident wave given by this thing, for reflected wave gives by this one relation, for transmitted wave gives by this one relation. Therefore, I don't need this equation and I want to rub them out and just write them down. J incident equals h bar k1 divided by m into A mod squared, and J reflected equals minus h bar k1 divided by m into B mod squared, this one relation, and J transmitted equals this thing, h bar k2 divided by m into C mod squared. So I rub these out too. Now, by definition, the reflection coefficient R is given by J reflection divided by J incident mod. And if I put the values from this in these equations, I get h bar k1 divided by m into B mod squared divided by, for J incident this value, h bar k1 divided by m into A mod squared, the whole mod. This cancels with this and the mod would convert this to plus, so I'm left with B mod squared divided by A mod squared. And from this relation, B in terms of the energy parameters in A is given by that thing, so B mod squared is in fact equal to K1 minus K2 whole squared divided by K1 plus K2 whole squared into A mod squared, and then this A mod squared. So this A mod squared cancel with this. Therefore, we write R equals K1 minus K2 squared divided by K1 plus K2 squared. This is the reflection coefficient, and let me write this here. I write R, note R to be K1 minus K2 mod squared divided by K1 plus K2 squared. And now the transmitted coefficient T is defined as T is the modulus ratio of J transmitted to J incident. And if I put the value from this equation in this equation, I get this equal to h bar k2 divided by m c mod squared divided by h bar k1 divided by m into m mod squared, the whole mod. H bar and m, h bar and cancel, so we are left with this k2 divided by k1 mod. So then according to this definition, k1 is a positive number, and according to this definition, since e is greater than v naught, k2 is a positive number. There, the mod of h bar k1 and h bar k2 is equal to k2 and k1, and then multiplied with c mod squared divided by a mod squared. And now, if I use the value of c mod squared from this one equation, I can further write this as k2 divided by k1, and c mod squared would become 2 k1 whole squared divided by k1 plus k2 whole squared, and then a mod squared divided by a mod squared. So this goes with this, and this will become 4, and k1 square would cancel with k1, so we would have 4 times k1 k2 divided by this thing. That is, t is in fact given by 4 k1 k2 divided by k1 plus k2 whole squared. So now we have all the parameters defined in terms of the energy parameters, and this is in fact the energy that describes the dynamics of the particle. From these two equations, if I add them up, I can write r plus t equals k1 minus k2 whole squared divided by k1 plus k2 whole squared, and then plus 4 k1 k2 divided by k1 plus k2 whole squared. And this I can write, if I open this squared, I can write k1 squared plus k2 squared minus 2 k1 k2, and since the denominator of the two terms is same, therefore I can put them into a single numerator by writing 4 plus 4 k1 k2 divided by k1 plus k2 whole squared, and this minus 2 k1 k2 with this 4 k1 k2 gives me 2 k1 k2, and that allows me to write this as k1 plus k2 whole squared divided by k1 plus k2 whole squared equals 1. This must be so. The sum of the reflection and transmission coefficient for every wave, for every combination of wave, or for every situation should always add to 1. Okay, now from this equation, if I look with reference to these two equations, k1 is always a positive integer, and k2 could be equal to 0 only if E equals V naught. If E equal to V naught, this gives me K2 equal to 0, and if I set K2 equal to 0 in this region, then I would have K1 squared divided by K1 squared equals 1. That is, under the condition E equals V naught, I have R equals 1. And when R equals to 1, under that condition, K2 equal to 0 gives me T equal to 0. So if the incident energy is exactly equal to the height of the potential step, then the transmission coefficient is 0 and the reflection coefficient is 1. That means everything is reflected, and that's what we have in the classical case. But if E is greater than 0, E is greater than V naught, then if E is greater than V naught, then K naught is never equal to 0. Then this term is not vanishing. And if this term is not vanishing, that means R cannot be 0. So for E greater than V naught, R cannot be 0. Mean there should always be reflection. And from the concept of classical mechanics, if the incident energy is greater than the height of the potential, then there will be no reflection. The particle will transmit into the second region. That is classical concept, that is classical approach. But we see that even if E greater than V naught, K2 is never equal to 0, and if K2 is never equal to 0, then the reflection coefficient is not 0. That is, quantum mechanically, it is possible that the transmission coefficient will always be non-zero. There will always be some reflection if the potential is there. Now let's see another case. If V naught is 0, if we mean there is no potential, V naught is 0, then K2 reduces to K1 because 2me divided by h bar square. And on that condition, K1 equal to K2. K1 equal to K2 mean R is 0. And if R is 0, mean the transmission coefficient is obviously K1 is equal to K2, and the transmission coefficient is maximum. That is, the reflection transmission coefficient must go to then 1. And under that condition, we in fact are dealing with free particle. If there is no potential, that is the dynamics, then this thing describes the dynamics of free particle. There is another condition that we can put on these two equations and also on this result, and that could be E very, very large than V naught. And if that's the case, then that means E minus V naught is approximately equal to E. And if I put this value over here, then K2 reduces again to K1. That is, this implies that K2 is approximately equal to K1. And when this is the case, then K1 minus K2 would go to 0 and there will be no reflection. And under that condition, again, that is the classical scenario, because E very, very large than V naught is a classical situation. So under quantum mechanical description, whenever there is a potential, whatever the value of potential may be, the reflection coefficient will never be equal to 0. However, under extreme conditions, the problem can reduce to potential to the classical situation. Otherwise, the description of quantum mechanical approach is different than the description of classical approach, in the sense that classical mechanics says there will be no reflection if the energy of the incident particle is greater than the height of the potential, whereas quantum mechanics says that no, there will always be reflection of the particle. So thanks for watching.